Okay, this is Andy Youngdahl's Csc578 final project video. My project was to build a convolutional neural network to learn to play Ms. Pac-Man, and I was going to use reinforcement learning with policy gradients to do that. So I guess we don't have much time, so I'm just going to rush ahead and get started. Basically, the emulator for the Atari Ms. Pac-Man is from OpenAI Gym. You can download that and install that. And I use TensorFlow to assist me in building the neural network. And what happens with basically the flow of the program is at each step you say, okay, OpenAI Gym, give me all the pixels on the screen. And then you decide what you want to do and you give it an action, which in this case is a number from 0 to 9. And that represents sort of the joystick directions, up, down, left, right, whatever. And then you do another step of the game and it just keeps stepping through that. So the neural network architecture here, on the left side we see we have a downsampled input, and these are the red, green, blue pixels from the screen, just like how I did with MNIST, where it gives you each pixel on the input. In this case it's the Ms. Pac-Man game board, and then I will feed that into a convolutional neural network. The first layer has a LSR 3x3, 16 kernels, stride of 2. Do some max pooling, and then another convolutional layer, same but only 32 kernels, more pooling, fully connected layer, 512 nodes, and then softmax output, which should predict the appropriate action at the appropriate time. Bit of note about the architecture: the pooling and the strides, the only reason I put them in there is just to make the graph computationally tractable on my system. I actually think it would do better without it. I also included dropout. I'm not sure if that was a good choice or not, but I hadn't had enough time to experiment with all the choices, so it's in there. So the next thing I want to talk about is weighting the gradients. Doing something like this, teaching a neural net how to play a video game, is in a lot of ways just like everything else we've been doing with classification. We have inputs, we run it through the neural network, and we get an output. The difference is this time the output is an action in a game. Whereas with MNIST we would say, okay, is the output correct or not? Let's calculate our error. With this we can't quite do that because we don't really know if the output is correct or not. So what we do is we just assume the action is correct for the time being, and then we complete the game. And then what we do is once the game is over, we can go backwards in time, so to speak, from the last game step to the previous, to the previous, to the previous, and we know all the scores for those, and we know all the actions, and we've been keeping track of all the gradients. So then what we do is we take a sort of a weighted score going back in time, where we take 99% of the score from the last step plus the current step, and just keep doing that over and over and over. And then we multiply that by the gradients we've saved. So sort of the effect this has is gradients or actions which ultimately result in a very good outcome will get boosted up very high, and gradients which end up resulting in a very bad outcome will get boosted very negative, and in between it's more indecisive. And then so we multiply all these weights by all the gradients, apply the gradients, and then do another game step. So ultimately what this does is encourage good actions, discourage bad actions, and drive softmax to select the best possible action for the best possible game state. So another thing we have to worry about in this sort of situation is exploration versus exploitation. The basic gist of this is we want to find the best game states, the best actions in the best game states, but we can't possibly go through all the best, all the game states, because there's far too many. So, what do we do? Well, remembering that our softmax output is all the nodes summed together between 0 and 1, and each of those represents the likelihood of the particular action being a good action down to not the best action. So what we can do to explore is we pick a random number between 0 and 1, and depending how that number comes out, we pick that action, whether or not it happened to be the best. So for example, if we only had 3 actions, Action 1 had 0.10 as a result, 2 had 0.20, and Action 3 had 0.70. Depending on the number that came up, if it was less than 0.1, we'd do Action 1. If it was between 0.1 and 0.3, we'd do Action 2. If it was over 0.3, we would do Action 3. So in this way, we gradually pick the better and better actions more frequently, but we always have the option to try something new to explore the game space a bit more. So we're already past 5 minutes, and we barely talked about it. But so results in future work. The network started out playing around 150 points a game. After 9,000 games, it's now up to between 275 and 325 points a game. Do a running weighted mean between 100 games, where each game contributes 1% to the running mean, and the running mean contributes 99%. So we don't want wild changes. So it has made some progress, although it is not a particularly good Pac-Man player. So what am I going to do since I'm obsessed with this goal? Well, first I got to double check all the code. This was a rush job to get it done in time. So I'm not absolutely certain that everything's working as it should be. So that's step one. Step two is to get a GPU and build a more powerful network. As I said previously, the network I picked was basically the most powerful one I could run. So improving that might improve the results considerably. I think it will. And then also there's various things called like actor-critic models, where you actually have two networks. One plays, and then the other one reviews and sort of decides what should be the best choices, the best policy to play. And then you feed these back and forth between the two models. I just wanted to really quick show you a quick demo of the game. There it is. It's playing right now. Let's see how it's doing. So you can see it's on game 9,947. Running means just under 300. It oscillates back and forth. And we'll go zoom in on Pac-Man right here. You can see that's the net playing. At each sort of move, it's feeding all the pixels in the front end, picking an action, and then from that action it's executing, and then it just keeps playing and playing and playing over and over. So that's it. Thanks for watching. Enjoyed being in the class with all of you, and I hope to see you all soon. Have a good evening.